Alright, this is the video on refraction, which will be our first video for treating light as a wave. We're calling it video 1 for now. I don't know if there'll be a video 2 for refraction, but if there is, then it'll be called number 2, and it'll follow after this one. So, refraction. Refraction is the bending of a wave when it is sped up or slowed down. So by changing the speed of a wave, we could change its direction. Now, how do we change the speed of a wave? Wave speed is dependent on the material that the wave is traveling through, right? So it's not really dependent on how it was made. It depends on what material it's traveling through now. So the speed of sound has a very specific speed in the air, right? And it doesn't matter if someone yelled loudly or yelled softly or tried to do something with a deep voice or a high voice, right? The speed of sound is pretty much a set value that's dependent on the air that it's traveling through, right? It has nothing to do with what made it. And that's the same with light. Light has certain speeds when it's in certain materials. And again, it doesn't really matter what frequency or wavelength or color the light wave is or where it originated from. It has certain speeds and certain materials. So wave speed is determined by the material that it travels through. Now, we could probably or most certainly find some exceptions to my general rules, but I would say in general, sound waves increase speed when the density of the material increases. Right, sound travels through the air at a certain speed, but if we went into water, which was more dense, sound goes faster. And light's really just the opposite. You know, the fastest light travels is in a vacuum where theoretically there's nothing there, and then it has a high speed. As we send it through materials that are more dense than that, then the speed tends to go down, right? Air, it's slightly slower, but it's still pretty close. It slows down some, but air is not very dense when we compare it to other things, right? We send it through glass, it slows down even more. We send it through diamond, it slows down even more. So again, as a general rule, light waves increase speed when the density of the material decreases. So even though refraction applies to any type of wave, we're going to use light because light's the easiest for us to experiment on in class. But if we see things happening with light, we could make the argument that these are the same types of things that would happen with other waves. So some of the equations that we're using here work with light waves, and if we were going to do it with something else, we would see some similar equations, some similar situations, but they would be slow. They would also be different in some ways. For example, so when we focus on the refraction of light, one of the important measurements that we care about is what we call the index of refraction. And with that said, I said it already, right? The less dense the material, the faster light goes. So the least dense material we could send light through is nothing. There's absolutely nothing there, so there is no mass. And that would be what we consider a vacuum. And in that case, then the speed of light is represented by a c, which is the fastest light can go. And it equals 3 times 10 to the 8th meters per second, right? So how fast does light travel? It travels at a rate of 1, 2, 3, 4, 5, 6, 7, 8. 100,003 million meters per second. Real fast. Nothing goes faster than that. Again, as far as I know. Index of refraction is a measurement, and every material we could look it up has an index of refraction. The symbol for index of refraction is N, little n, is our symbol for index of refraction. And it is by definition the ratio of the speed of light in a vacuum over the speed of light in the material we're talking about. And we'll do a few examples with that. But we know what C is. C is always this number. So the only variable is really the speed of light in that material. So we're going to have a lab later on where we find the index of refraction, and we're going to do that without actually measuring speeds of light. So we're going to look at, its effects on a light wave and how the light wave is bent. So we're going to certainly look at some of these things, but this is what it is. N is the speed of light in a vacuum over the speed of light in that material. Okay, let's go to some examples. All right, so let's say we have this material, we have this type of plastic, and we measure the speed of light in that plastic, and we're saying that the speed of light in the plastic is 2.7 times 10 to the 8th meters per second. What is the index of refraction for that plastic? So we know the equation, I'm going to write it a little bit abbreviated. N equals the speed of light in a vacuum, which is c. C stands for the speed of light in a vacuum, over v, which we haven't really talked about speed, but speed is represented by a v usually, and we'll say it's the v for that material. So it's going to be 3 times 10 to the 8th meters per second divided by 2.7 times 10 to the 8th meters per second. And we're also checking the units a little bit. We're going to do unit analysis down the road without a doubt. So it's something that we'll start talking about soon. But I see seconds cancel out. I see meters cancel out. So this is a unitless dimension, and that makes sense because it's a ratio of two speeds. So the units all disappear. So if I do this one out, I get 3 divided by 2.7, and I get 1.11, and that would be the index of refraction for this plastic. Now, a couple things to point out. C is the fastest, well, one thing to point out. C is the fastest light will travel, period. So I always know that C is the biggest number possible. So any number I put under it, well, it could be the same number, 3 times 10 to the 8th meters per second, which just means I have an index of refraction of 1. But if it's not that, then it's some number less than that. So the index of refraction could never be less than 1. It's impossible if I have an index of refraction of less than 1 because the top number of this fraction is the biggest possible number we could put into this equation or into this ratio. So I always expect an index of refraction of greater than 1. And the bigger the number gets, that means the smaller this number is, which means the more it slows down light. So if we had something, and I don't think it exists, but if we had something with an index of refraction of 10, well, then that means it cuts down the speed to 1/10 of what it was before. It cuts it down an enormous amount. So that's what we're talking about. Example number 2, water has an index of refraction of 1.33. How fast does the light travel in water? Okay, so it's the same equation. Let me go back to my color palette here. And what do we know? Well, we know N and we know C, and we're looking for this. So if I rearrange this equation, multiply both sides by the speed of the material to get it out from underneath the fraction, and then divide both sides by the index of refraction so I can get the speed by itself, I have 3 times 10 to the 8th meters per second divided by 1.33, and that one I could do, and with some rounding in there, and of course a lot of these times we're going to have to round, 2.26 times 10 to the 8th meters per second, and that's how fast light travels in water, because water is a more dense material. It slows down the light as the light is trying to pass through there. So there's 2 quick examples with index of refraction. It's not really, we're not going to spend a ton of time with these types of calculations. The point of these examples is to kind of show us how we get N and how we could use N to determine the speed in a material. But that's, really we're going to focus on refraction, how light bends because of this change in speed. So this just helps us come up with a value that deals with the change in speed. All right, so the bending of light when it is sped up or slowed down. So what I like to use is I like to use a car. And this title says when light bends, but I'm going to pretend we're not talking about light first. I'm going to pretend we're talking about a car. And I don't need to know everything about the car, nor do I need to actually draw the whole car. Really, all I'm going to draw are my 2 front wheels. There they are. So we're going to pretend that those are the 2 front wheels of my car. And when I want to figure out how a wave bends, I got to ask myself 2 questions. First of all, which wheel is going to hit the other material first? And then the second thing is that new material going to speed up or slow down the car? So as we look at this, I'll say I have wheel number 1, I'll say I have wheel number 2, and this car is traveling this way. So it's on the fast material, which we could say is a road, and it's going to go into the slow material, which we could say is something like sand or mud. Now, as I look at this, these wheels are going to go. Wheel 2 is going to hit the slow material first. So we're going to say that wheel 2 is here. Now it's in the slow material. Wheel 2 is in the mud. and wheel 1 still on the road. Those wheels don't look as good, but that's okay. So what's going to happen? Wheel 2 is going to hit the mud, and it's still going to move, but it's going to move very slow. It's going to move like this far. But wheel 1 is still on the road, still has traction. It's going to be able to move quite a big distance, so it's going to move something like this, which is going to cause this whole thing to pivot. Now the wheels, when they're both in, they're the same speed. It's just going to go back to going straight. But if we imagine this whole thing, these two wheels pivoting clockwise in my example, and then they start going off straight again, then that means that this whole thing is going to shift also. And now the new path is going this way. So where the car was traveling in this dotted line, it is now traveling lower at an angle lower than its straight line path. We could say it was bent downwards, if you will. So there is my first example. Now, if we do it again, this time we're saying we're in the slow material, and we're going to start going into the fast material. And I'm going to say that this is wheel number 1. I'm going to say this is wheel number 2. I'm going to say we're going this way. We start going. Now, wheel number 1 is going to go into the fast material first. So if it's like this to start, then wheel number 2 still in the slow material. It's still kind of stuck, if you will. Wheel number 1 is in the fast material. So yeah, this is going to move forward, but it's going to move forward slowly and just a little bit. And this one's going to move forward a lot, which is going to cause this whole situation to rotate counterclockwise, because basically 1 is still moving around 2 because 2 is going so much slower. And then when they're both in the fast material, because 2 is going forward, then it'll go off in its new direction, so it would rotate like this. So this means in this case we could argue that it would pivot or rotate to the right from the original path. As long as you see it, I care what word you use. I mean, we kind of have to decide. So this would bend as shown. Now, with that said, let's say we had this situation where we have the front of the car and it's in the slow material, it's going into the fast material. But to be honest with you, for this one, it doesn't matter if we're going slow, fast, or fast, slow. Because as we look at this and we have my two wheels and we say, okay, well, which one hits the new material first? Well, if it's going straight down like this, so it's perpendicular, well, then fine, both wheels hit at the same time, which means both wheels speed up at the same time, which means we don't have this process where one wheel's faster than the other and we pivot. So what's going to happen? Well, here we don't see any bending, right? So this is the one situation where speeding up or slowing down the wave doesn't actually cause it to bend. So there's kind of my 3 examples of how light bends, and that's really one of our goals. We're definitely going to do calculations to determine how much it bends. But just with this analogy, we can kind of see the direction that it bends, and we could see what are the important characteristics that allow it to bend or would make it bend a lot or make it bend a small amount. So the actual bending itself depends on a few things, right? How much can we bend the light? Well, that matters. A couple things matter. One, the angle that the light strikes the surface definitely matters, right? When I look at this one, right, it's striking perfectly perpendicular, and it doesn't bend at all. Whereas these that are coming in at an angle could bend quite a bit. And if we have more of an extreme angle, right, if I had a situation where let's say that this was my surface, and it doesn't really matter, also I'm going slow to fast, and this is the path that I'm taking, we can definitely make an argument that the bottom wheel, wheel 1, is going to hit the fast material soon, and it's going to bend a long ways before this one starts to get into the other material, right? Because it's just the way it's oriented. So the angle of entry definitely matters. The other thing that matters is the materials that we're talking about, right? How much is that object, or how much is that wave sped up or slowed down? And again, we're talking about light normally, so that, we're talking about the index of refraction of light and so on and so forth, right? So the difference in speeds makes it different. Do we go from something that's slow to something that's faster, but not much faster? Well, then we won't see much bending. But if we go from something that's slow to something that goes extremely fast or incredibly faster, well, then we expect to see a lot of bending. So we care about the angle that the light strikes the surface, and then we also care about the difference in speed. How much is speed going to change when it goes from one material to another? Now, there is an equation for this, but again, not too worried about the equation right at the moment. But let's say we had this situation. Let's say that we had a ray of light And that ray of light is coming in like this. And right now we're just going to focus what it does when it enters this material. So let's say we have something like a plastic, 1.42, it's like a plastic or a glass, and we want to know how the light bends. It was going horizontal, what path does it take when it hits this plastic? Well, again, we could put the wheels on, and I know light waves don't have wheels, but the wheels work, right? So we could say, okay, well, the bottom one hits the plastic first, and that one's the one that's going to get slowed down, and the top one is still going fast, so it's going to rotate like this, which means instead of going in this direction, it will now go in this direction, right? So it'll bend downwards. Just the opposite, let's say we're shining a light, and we're shining a light underwater. So we are in the air, we're in the water. And the light hits an air bubble. Now we could argue the bottom wheel would hit first, which would cause it to rotate counterclockwise, which would mean it would take a upward path and would get bent upwards. And again, how much upwards? Well, we'll do math to determine exactly how much does the path change, but we're not doing that right now. Right now, we just want to focus on the fact that light bends, and it bends because of the entry, the angles with respect to the surface and the material change. So what if we had something like this? And this is more of an approximation of a convex lens. Convex, because it's bowed outwards. So it's called a convex lens because of its shape. And if I made a real convex lens, and it's important that we understand a real convex lens, it wouldn't be all straight lines. It would be exactly no straight lines. It would be curved, right? So it would bow outwards and then inwards, and it would bow outwards and then inwards, right? So the whole thing would be curved. So understand that. This is kind of just an approximation to keep the lines straight, just to make it easier for now. But we would need to shape this a very specific way, and that way would look like this in general, but it would look more like this specifically, right? And actually the actual curvature and everything would matter drastically. But in general, let's say I have this plastic lens or a glass lens or anything that slows down light, and it's shaped somewhat like this. And I have three rays coming in. I have this ray, which is coming in horizontal, hits the top surface. I have this ray, which is also coming in horizontal, hits the middle surface. And then let's say we have this one with cool effect lines, and this one hits the bottom surface. Now, we're going to start with the top one. And when it hits here, and when it hits over here, we are going to look at both places. So it comes in, if we draw our wheels, bottom wheel would hit first, it would slow down, cause this whole thing to rotate so that the light is now going lower than before. And how much lower? Again, we need some equations for that, but let's say it does this. And then if we put the wheels on again, and even by drawing the wheels, we could see that the top wheel would hit the air first, but that would cause it to speed up, which would cause it to rotate down again. So it would go something like this. So we could argue that here, the light would bend down, and then here, the light would bend down again, and that says down, even if you don't believe me, right? So light bends down and down. So as light enters and exits this convex lens, when it enters, it gets bent downwards. When it exits, it gets bent downwards again. So when it leaves, it's going down. And once it's the air, it's not bending at all. It's not changing speed. Now this ray of light that hits the dead center of the convex lens, well, that ray of light, both wheels hit at the same time, both wheels hit at the same time, and it would keep going straight. Now again, the surface is really bowed. It's not like a big flat surface in the middle. So we can make the argument that everything above this middle line bends downwards. And then what do we see when we hit the bottom part? Well, again, I could put the wheels on it. Top wheel hits first. That one slows down, so it's going to bend upwards. And then if we put the wheels again, the bottom one's going to leave first and go faster. So again, it's going to bend upwards. So instead of going in this path, it's going to bend more like this. So we have a situation here where all the rays of light at the top of the lens get bent downwards twice, but in the overall effect is it gets bent downwards. And all the rays at the bottom half of the lens get bent upwards. And if we shape this correctly, then we have this point right here. And all the rays of light converge at that point. Now, again, that point's there if we make the lens well, but we could make a lens so all of the stuff bends at the same amount so they all cross at this middle point, right? Which is part of what a lens maker does. He does a good job making it, so this happens. So this is called the convex lens because it's bowed outwards, but it's also called a convergent lens because the rays of light converge on the other side. And these rays of light cross at what we call the focal point. And the focal point's important because we're not going to say all rays of light cross there. And even if you watch this video and even when you're in class, still someone's going to say it. Say, oh, well, those rays of light all go through the focal point. No, not every single ray of light goes through the focal point. What rays of light go through the focal point? Well, the rays of light that go through the focal point are rays of light like this. These are rays of light that are hitting the lens perpendicular. This lens is oriented vertically. The rays of light are coming in horizontally. And these horizontal rays of light, no matter where they hit this lens, they'll all cross at the focal point. But if I had a ray of light like, let's say this, well, that's not crossing at the focal point. Sure, it's going to bend, but it's not going to bend so much it goes through there, right? Or if I had another one that was going like this or another one going like this, I could spend all day drawing them, right? They're not going to go through the focal point because they're not coming in horizontal. So this focal point is where these horizontal rays of light cross, or we could say the focal point, and it's an important place, so we've got to understand what it means. Is where rays of light cross if they are perpendicular to the lens. Right? So these rays of light are coming in horizontal, the lens is vertical, they're striking it perpendicular, they're perpendicular to the orientation. I mean, I could kind of write to get this more and more specific, but it's more important we understand. So these rays are coming in horizontal, the lens is oriented vertical, and therefore they're perpendicular, and those rays of light will all cross, whether they're coming in from here or up here. As long as they're horizontal and the lens stays vertical, they're going to cross at the focal point. Now, along with the focal point, there's another important thing to note, and that is the focal length. And sometimes they use these words interchangeably. I might say, hey, it has a focal point of 10 centimeters. Well, that means the focal length is 10 centimeters, right? So what's the focal length? The focal length is from the center of the lens to the focal point. And the focal length is important because objects, lenses are sorted or paid for, however you want to say it, right? When we buy a lens, what do we know about it? We know its focal length. If you go to the eye doctor and they write an eyeglass prescription, what are they saying on that eyeglass prescription? They're really saying the focal length. Now, eyeglasses work with diopters, but if we knew what the diopter was, we can convert that directly to a focal length. So why they have diopters, I don't know. They decided just not, to change it up a little bit, right? But what is it? It's just another way of giving a focal length. If you have a camera, you're like, oh, my camera has a 35 millimeter lens. Well, what does the 35 millimeter means? It means that's the focal length, right? And if you had if you were like fixing a telescope that was broken, you were like, oh, I got to go to the store and buy a new lens for it. What would you have to tell them? Well, you'd have to tell them the size so it fits right. But the other thing, just as important, is you'd have to tell them the focal length of the lens you need. So focal length is an important thing because it's always telling us, how good the lens is at bending light. And that's the whole point of having a lens, is to bend light, right? So a lens with a small focal length bends light a lot, right? If the focal length is right here, let's say, well, then that light's got to get bent down a lot. This light down here has to get bent up a lot so it crosses there. A lens with a very big focal point means that all the rays of light cross like way out here, which means it doesn't bend light as drastically, right? It travels quite a distance before it actually gets bent, downward so much that it kind of passes through this center line. So Focal length is very important because it's really how we classify lenses as strong lenses or lenses that bend light a lot to lenses that bend light a little bit. We're going to look at this convex lens and convergent lens, but we are going to go to video number 2 for that.